Okay, so the next set of problems are 15 and 16. So I'll go ahead and do 15, and you guys can do it again, or if you have already, you can do it again as you guys do the homework, because these are good proving problems. Okay, so 15 is, by definition, we have that A is congruent to B mod M. So if we have this, then this implies we usually write it as the right-sided arrow with double, and this implies that M divides A minus B. So this was one of the definitions, and this also implies that A minus B is K times M, or some K that's going to be an integer. Okay. So here I can add B to both sides, so I have A is B plus K times M. So this shows us that A mod M equals to B plus KM mod M. And this, by also one of the theorems in the book, this is also B mod M. And we're done. So this was 15, and 16 is pretty similar. It's just going to the other direction. So it's kind of like you guys are starting here, or starting with this statement, and trying to get back to A is congruent to B mod M. So give it a try, and let me know if you guys are confused with these proving problems. Okay, so 21, I wish this problem had appeared earlier, but I think at this time you guys all know how to do this, but just go ahead. So I think I assigned 20, which is very similar to 21. Alright, so 13 mod 3. So you guys can do this as 13 divided by 3 and find the remainder, and that remainder would be the answer for this. But that might not work smoothly when we get to the negative numbers. So I'll tell you, I'll do this by using the actual definition. So 13 mod 3, we start this as 13 equals to 3 times some number plus a remainder. So in the book it says by definition our remainder always has to be a positive number. Okay? So if we start thinking 3 times 3 is 9, we need to go bigger. 3 times 4 is 12. So if we had 4, we would have a remainder of positive 1. If we go up more, so 3 times 5, that's 15. So our remainder is no longer going to be a positive number. So there we go. Our answer is 4, and 3 times 4 plus 1. So this answer is, our remainder is 1. Let's use this logic to find the negative number. So negative 97 mod 11. So I'm going to start this writing out as negative 97 equals to 11 times some number plus a remainder. Again, the remainder always has to be a positive number. So I start to think this has to be a negative number, right? Because our answer is negative. So think this is a negative, and if I think 10, negative 10, 11 times negative 10 is negative 110. That's too big. What about 9? Negative 9 would give negative 99. So we would have to just add 2 to make this equation work. So this is remainder of positive 2, so that's the answer for B. Part C is 155 mod 19. So this, I start writing it out again. So 155 is 19 times some number plus a remainder. So I start to play around with some numbers, and it seems that 19 times 8 plus 3 would work. So therefore, This is our 3. With this positive numbers, you guys can just go ahead and do this too. 155 divided by 19 and do the math, and the remainder is going to be 3. Let's do one more negative number. So this is 221 mod 23. Okay, so by definition, I can start writing this down as negative 221 equals 223 times some negative number plus r. And this negative number is going to be negative 10, because that's going to give us a positive 9. And if you do negative 9 or negative 11, you'll either get a too big remainder, bigger than 23, or you're going to get a negative remainder. Okay, so therefore this is 9. I'll write these process up again nicely and post the solutions in as a PDF file as well. Okay. So the next problem, I'll go over 29, which is similar to the assigned problem of 28. So part A, we have to decide whether each of these integers is congruent to 5 modulo 17. Alright, so let's check. 80 equals 2, or is congruent to 5 mod 17. So this, we have to check, it's 17 divisible by 80 minus 5. Okay, and I'm using the definition. I think this was theorem 4 in the book, and it also has a good proof that you guys can read. And we know that this is not true. 17 is not divisible by 75. So therefore, the answer for A is no. Let's do B. So 103 is 5 mod 17. So this, we can rewrite this as 17 divides 103 minus 5. Again, applying the straight definition, and we're trying to see if this works. Okay, so the 17 divides 97. This is not true, so therefore also B is no. Right, so we have, next one is a negative number, so negative 29 is 5 mod 17. Applying the definition or theorem, we have 17 divides negative 29 minus 5. Is this true? And this, the 17 divide negative 34, and yes, this is true, so yes. And lastly, negative 22 is congruent to 5 mod 17, right? And so this is going to be 17 divides negative 122 minus 5. Let's check. 17 divides negative 127. And this, it does not divide. It does not give us an integer number, so this is no as well. I'll write up a solution for this as well in the same PDF document, then I will upload. Okay, so the last problem is let n be an integer. Prove that. So this, I was looking at problem 40. I think that's one of the problems. Yeah, so I assigned problem 40 and I couldn't really find a similar problem in the book, so I'm gonna use this example, which I think it's pretty close. Okay, so let's prove this. And for problem 40, which is similar to here, you will have to prove by cases. Okay, so the first case, integers are a mix of, or compilation of the odd numbers and even numbers. So we're gonna use that. So the first case is when n is even. Alright, so let's suppose n is congruent to 0 mod 4. Okay. And n is even, which means that n is 2k for some k that's going to be an integer. Okay. And n squared is going to be 2k squared. It's going to be 4k squared. And so this, by definition of congruency, we have n squared is congruent to 0 mod 4. Alright, so that's taken care of. Let's go to case 2, where n is odd. So if this also works, then we have proven that these two cases are true. Alright, so to prove this, I'm going to suppose that n is congruent to 1 mod 4. Okay. And this makes sense because if we're trying to divide something by 4, if it's an odd number, then we're going to get the remainder of 1. Okay. So if n is odd, then we have 2k plus 1. So we have n squared equals 2k plus 1 squared, which is going to be 4k squared plus 4k plus 1. And I can take out the 4, and that's going to be k squared plus k plus 1. Alright, so we know that this is divisible by 4, and we are going to still have 1. So therefore, by definition of congruence, we have n squared is congruent to 1 mod 4. And we can check also by cases. So this is the formal proof. And let's go over some of the examples if this is true. So if we have 0 squared, this is going to be 0, which is congruent to 0 mod 4. If we have 1 squared, this is 1, which is congruent to 1 mod 4. If we have 2 squared, this is 4. This is congruent to 0 mod 4. And we do 3 squared, this is 9, which is congruent to 1 mod 4. Let me do one more. We have 4 squared, this is 16, which is congruent to 0 mod 4. So by looking at these cases, I think we can nicely wrap up by saying that n squared is congruent to 0 mod 4, and also n squared, it's either this or 1 modulo 4. Alright, so try number 40 as your proof, and I think that's it.